Okay, good afternoon, everyone. Good afternoon, sir. Can you hear us? Api Singh, sir, can you hear me? Okay, okay. RP Singh, sir, can you hear us? So we will wait maybe. Hello, sir, can you hear us?
Yeah, I can hear you.
Okay, okay. Thank you very much, sir. So we are now starting this session. Just I'll make sure that the recording and everything is done.
Okay.
Recording and everything is done. This camera. Okay. So I welcome to all the participants in the QT-06 series. Today is the 8th September, and today our speaker is Professor R.P. Singh, who is associated with the Atomic Molecular and Optical Physics Division at Physical Research Laboratory, Ahmedabad. His area of research includes light scattering, phase singularities of the light, nonlinear optics, quantum optics, and quantum information. Presently, he is engaged in the experiments on the high-dimensional entangled state, free space quantum communication, quantum imaging, and quantum radar. Working on the DST-funded project, Free Space Quantum Communication, Road to the Satellite Quantum Communication, he has already demonstrated free space quantum key distribution over the 200 meters, and he is presently occupied with other aspects of the satellite-based quantum communication. I welcome you, sir.
Okay, let me share the screen. You can remove that.
Yes, we can see your screen, sir.
You can
Oh,
see
no,
my...
now you can share, yes.
Yeah.
Now you can share.
You can see my screen now?
Yes, yes. We can see
I
the
will...
screen, sir.
Okay, I will make it full. It's fine now?
Yes, yes. Now we can clearly see. Yes, sir. You can start.
Okay, thank you for asking me to give this webinar. Though I'm not very comfortable with webinars, I prefer in person. Anyway, So I am supposed to talk to you about free space quantum communication. But before we go for free space, we will discuss what is quantum communication. By the way, whatever I am presenting is like collective contribution. So many students, postdoctoral fellows, PhD students, postdoctoral fellows, engineers, and younger colleagues have contributed to this part. Okay, and we have a very vibrant program at PR under Quantum Science and Technology program. So we have many labs working in different verticals of quantum technology that includes quantum materials and devices, quantum computing, quantum communication, quantum sensing and metrology. So we cover almost all the verticals of quantum technology at PRL under this program, Quantum Science and Technology program, which comes under atomic, molecular, optical physics division of PR. So what is quantum communication? When you communicate through quantum states, that's quantum communication, and information is coded in terms of quantum state, okay, when you are communicating. And in general, it's qubits. Okay, qubits the basic unit of quantum information. You can have qubits also, qubits, q-quarts. D means any dimension, but in general, it is qubit because defining qubit or making qubit is simpler, and controlling qubits, manipulating qubit is simpler compared to high dimensional quantum states. Since we're using quantum states, qubits, so it follows laws of quantum mechanics. Okay, so your communication is governed by laws of quantum mechanics, and because you are using laws of quantum mechanics, it provides unconditional security to communication. And we are going to talk mainly of quantum key distribution, which is one of the very popular, very visible, ubiquitous application of quantum communication. So here you can make keys and distribute the keys, encryption keys. You can make encryption keys and distribute them using quantum mechanical principle. And you know very well that encryption keys are required to access and distribute it securely so that only intended party can decipher the information or decipher the message. So it's going on since ages, like you have key, you encrypt the message with key, and then intended party decrypts the message using the key. So it's going. But using quantum mechanical principles, you can make it much more secure and much more secure against quantum computers. So urgency of secure quantum communication is due to threat perception from quantum computing. So once you have quantum computers, so present day encryption. Now also you use encryption. It's not like that you are not using. As I told, it's going on since ages, centuries. People do use encryption and decryption for securing the message, securing the communication. So our present day encryption scheme that makes like making of key and distributing the key, that will be compromised once we have quantum computers, and using quantum algorithm like Peter source algorithm and other algorithm, Grover's algorithm, the present day encryption system can be compromised. That becomes returned. So that is the very big threat to communication or communication, you can say, because your keys will be compromised, so your messages, your communication can be deciphered. So even unintended party can have information which is not required to be revealed to those parties. Yeah. So that is the problem. That's why this quantum key distribution becomes very important. Okay? Securing your communication using quantum keys made by quantum mechanical principle and distributing them using quantum mechanical principle. So what are those quantum mechanical principles which are used here? These are the superposition of states, entanglement, and no cloning theorem. These are the basic principles which are being used for this securing your communication. What is superposition of states? One may ask. So, this cartoon can explain what is the superposition of state. We will discuss in more detail this superposition entanglement as we go on. So, you can see here this cat is there in the box along with this poison bottle. So, as long as you don't observe, like opening the box, you don't see after opening the box, you can't say that whether cat is dead or alive. So cat is in a superposition state of dead and alive. Okay. So that's a superposition state of dead and alive cat. Now you have poison bottle. So if poison bottle is broken and it's poison, so cat has to be dead. And if poison bottle is not broken, so cat has to be alive. Okay. So here, if you know that poison bottle is broken, so cat is dead, means state of poison bottle and the cat are strongly correlated. Okay, so this kind of strong correlation that is called entanglement. Okay, but you can see if you apply these things to macroscopic objects like cat, it leads to absurd result. If you keep a cat there in a box, either it will be dead or alive. It can't be in the position of both like. So it's absurd results it leads. But when you go to quantum mechanical system, that becomes a very interesting property, and you can utilize this property to your advantage. I will give you example of a photon. Suppose there is a photon, single photon, and it in it is incident on a beam splitter. It's a single photon, so it can either transmit or reflect. Okay. Now, so it's a superposition state of both reflection and transmission. If you put PBS, polarizing beam splitter, what polarizing beam splitter does? It transmits horizontal polarization and reflects vertical polarization. So it is in a superposition of horizontal and vertical polarization, that photon. Okay. And once you measure, suppose you put a polarizer just to check after PBS, suppose either in path of transmission or in reflection, you put a polarizers to measure. You have now photon is there, so other path you will not see any photon, so it has gone. But you can compare this with classical light. Suppose you have a laser beam, it's falling on, suppose it's falling on a beam splitter, so it will be transmitted and reflected. Suppose you measure in the transmission path. Okay, you can measure power and still there will be power. This is also superposition, but it's a classical superposition. But in reflection path also there will be beam almost equal because it's beam theta. But in quantum, it's a single photon, it's quantum system. Okay, that's why the photon, the moment you say photon, it's a quantum mechanical system. Okay, and that's why once you measure, it's gone. Okay, only one path you can see that, right? Single photon. So that's kind of superposition we talk up in quantum mechanical system, and it's very interesting. And entanglement, you will see entanglement is also kind of superposition. Here, there are two things. Okay, two poison bottle and dead cat, cat and poison bottle. So it's a superposition state of two systems. So it's a special kind of superposition state where two bodies are involved or two systems, two subsystems are involved. we'll discuss more about entanglement. Okay, and so why this quantum key distribution is becoming important? Because classical, when we are doing this classical communication, one can intercept the information, or one can tap the wire which is carrying your communication, store the information, okay, encrypted information. And once you have quantum computer with sufficiently powerful quantum computer which can run quantum algorithm, you can break that encryption and can have all the information which was stored there. So one can intercept now and decrypt it later. That's why this urgency for quantum key distribution. And which are the customers, like defense, very important, okay, health sector, where you store the critical data pertaining to personal health and all. Suppose prime minister's health records are very important, nobody should know, or president. So these things are very important, it has to be secure. Bank and financial institutions, all your financial transactions has to be secure. So fine. So an existing, let me see. So an existing optical link cannot be automatically be assumed to be compatible with QKD protocol. Okay. The optical link is there. We are communicating through fiber and optical signals. They carry optical signals. And when you are using quantum key distribution or quantum communication, it cannot be used the same way. Why? Because optical amplifiers, rotors, and transceivers will destroy the information encoded in quantum states. Okay, so this I entanglement and no cloning. No cloning is very important. Entanglement, I told you what is. No cloning, I don't know. Some slide is missing there. So no cloning is an arbitrary quantum state cannot be cloned. Okay, cannot be copied. Okay, so this is very basic principle providing security to quantum communication. So if you are sending your information through a quantum state, it cannot be copied. That is ensured by no cloning theorem, which is very basic to quantum mechanics. So, but it creates problem also. Problem in the sense, here you see, when you use a normal optical communication, okay, after certain kilometers, 10, 20 kilometers, you use boosters or amplifiers to amplify the signal. Okay, but when you're using quantum, when you're doing quantum key distribution or quantum communication, you cannot amplify, you cannot boost the signal, because you can't make copies of the quantum state, unknown quantum state. That is the problem. So that's the trouble also, although it provides advantage, but that is one of the troubles also. So how one goes about this quantum key distribution requires single photon source and source of entangled photons. One can use a discrete variable as well as continuous variable. Discrete variable like polarization as two states, polarization, horizontal, vertical, diagonal, anti-diagonal. Or one can use orbital angular momentum states of light. One can use time bin. Okay, means arrival time. You can fix a time window where the photon is arriving there. So that variable also one can use. One can use frequency as a variable for entanglement. So there are so many variables one can use, and they may be continuous or discrete. And once you have use these variables for encoding information, and they can be communicated through free space or fiber. Okay, because light can go through both free space as well as fiber. So, however, current optical fiber and photon technology, quantum communication is limited to the order of few hundred kilometers only. As I told, no cloning theorem uh, creates rubble also, because optical fibers will have attenuation. Okay, and you are sending, when you are talking of quantum key distribution or quantum communication, you are sending your information through photons. And since they have attenuation, this signal which is going through photons, they will be lost, and you can't use amplifiers. So that is the problem. That's why with optical fiber, you can't have quantum key distribution or quantum communication for very long distances. I have written detectors also. So detectors will have certain efficiency. Okay, and for certain wavelengths it will have higher efficiency, for certain wavelengths it will have lower efficiency, they will have certain dead time. So our this communication is limited by optical fiber as well as detection system also. It's an engineering challenge basically. So we can't, using fibers, we can't have quantum communication for very long distances, and that's why one will have to go for satellite based quantum communication. Okay, if you want to have long distance quantum key distribution or quantum communication, one will have to use satellites. And satellites, using satellites, one can have communication for thousands of kilometers. Okay, but before we go for satellite, one has to use like few hundred. One has to check the system whether it's working fine or not, whether your protocol we are designing for distributing, making the key and distributing the key, whether that is fine. There any security loophole there. All the equipment which we are using, they have to be well characterized for security purpose. So all those things. So first you do for a few hundred meters, kilometers, then you go for satellite-based quantum communication covering thousands of kilometers. And in fact, if you want to have quantum network, quantum communication network, one will have to use both optical fibers and satellites. Okay, one has to combine both if you want to have quantum communication network. As I told, one can use discrete variables as well as continuous variable. I'm talking of photons, but photons are lights. So you can ascribe electric field to the photon. Okay, electric field to the photon you can ascribe. And once you are using electric field, it's a continuous thing. Amplitude is there, phase is there, because now you are talking in terms of field. So amplitude and phase are continuous variable, unlike like polarization or orbital angular momentum of light. So you can use both discrete variable as well as continuous variable for quantum key distribution or quantum communication. We have prepare and measure quantum key distribution protocols, where you prepare a quantum state and then you send to the receiver, and receiver measures. So, and by this sending and measuring at the receiver end, one can have keys at both the ends. Okay, and these keys can be used for encryption and decryption. So here, prepare and measure, you have two very popular protocols, BB84 and B92. BB84, BB stands for name of scientist, Bernard Arts, and this is by Bernard B. And these are the years when they were discussed for the first time. You can have entanglement-based protocol under discrete variable category. And the very popular protocols, or one of the very popular protocols, are BBM 92, okay, and Eckhart 90. So BBM 92 was given in 92. Here, this along with BB, there was Marmin, another scientist. That's why BBM. And then Eckert, Arthur Eckert was the scientist who proposed this protocol in 90. So in entanglement-based protocol, you have two entangled photons, and they are distributed to two parties which want to communicate securely. And both the parties do the measurement, make measurement on these photons, and by making measurements on the photons, they develop the key. Okay, and with those keys, they can do the secure communication. Same way here, prepare and measure protocols. Like one party prepares the states, quantum state, and another party measures that. Okay, and entanglement based. So here, when we say entanglement in continuous variable, so we use squeeze states of light. That is, one can have entanglement, one can observe entanglement there. We squeeze the light. And here this protocol is called Gaussian modulation based. Okay, this is GG02, again name of scientist, 2002 it was discovered. Croissants and Grangier, these were the scientists. And this is Gaussian modulation, where you modulate the phase and amplitude both, and that modulated signal is sent to the other party. Like suppose Alice is one party, Bob is another party. So Alice prepares these states, quantum states, modulations, and then sends to Bob, and Bob is. So I'm a discrete modulation based here. Okay, this is you modulate the phase in a discrete way here. That is discrete modulation based protocols. So quadrature phase shifting is one of them, and quadrature amplitude modulation. So there are many others. These are the two popular. So, but in our talk, we'll be concentrating on discrete variable quantum key distribution. Although in our lab, we do both continuous variable quantum key distribution as well as discrete variable. You may wonder why I'm talking of quantum key distribution only, not other aspects of quantum communication. Although quantum communication is very broad, as told, any communication using quantum states is quantum communication. It's a very broad area. It covers like quantum teleportation, quantum secure direct communication, okay, and entanglement swapping, quantum repeaters. All those things come into this quantum communication. Even these quantum computers, they will have they have many nodes, and quantum states are being transported from one node to another node. There also you talk of quantum communication. So it's very broad area, but we are concentrating on quantum key distribution only, because somehow still not many experiments have been done related to other aspects of quantum communication. So this is the most visible, most ubiquitous application of quantum communication. So I mentioned you for longer distances, one will have to use satellites for quantum communication or quantum key distribution, and you can use satellites for prepare and measure quantum key distribution as well as entanglement based quantum key distribution both. So when we are using it for prepare and measure quantum key distribution, you prepare states in the satellite. You have a system where states are being prepared and they are transmitted to the ground station, another party. Suppose this is Alice, this is Bob, Ram or Sita, whatever name you can give. So there are two parties. So here they are being prepared and being transmitted to the ground station. Ground station is basically an optical telescope which can receive the optical signal. Okay, and you have measurement devices at the ground. Okay, and so, that's what. So once, and then they can have key Ka and K. This is the encryption key they have developed by prepare and measure protocol. Same way, like satellite is revolving, rotating. So it goes to another station in its path, like in its orbit. It signal goes to another station, and that station develops the key KB. By communicating to that station, satellite develops a key KB. Now satellite is having this key KA and KB, both keys are there in the satellite. So one can have this jar operation between these two keys K and KB, and this jar operation or encryption thing. These two keys can be encrypted again, and one can send it to the ground station, one of the ground station. Another jar operation you see here, another jar operation using this KB will give you the KA. So now this ground station B is having both the keys KA, because you have done this jar operation with KB. KB is here at the ground station. This B ground station is having KB. You know that. And now you have sent this jar KA and KB jar that you have sent to ground station B. And now with KB, another operation, this station will have key KA. So now both the stations are having this, ground stations are having this same key, and they can have now quantum encryption and decryption. So because they have quantum keys, that's why we call quantum cryptography. So one can encode information using this key and then send it, and another party can read. And this kind of communication is called a trusted node, when you're taking satellite as a trusted node. Okay, because satellite is having key information, and it can be relayed, or somebody can hack the satellite memory and can have information, okay, about the keys. So you have to trust that nobody is going to hack my satellite. Nobody, like, there is no malicious device which is passing on information about the key from satellite. Satellite manufacturer can put some device which can transmit like this, can keep it to some other party. So, but you have to believe, like, you have to trust on satellite, that satellite is not passing, nobody can hack, and satellite is not having any device. This kind of communication is called satellite as a trusted. Or when you do this prepare and measure quantum key distribution, most of the time your node, you take it as a trusted. But suppose satellite is having entangled photon source. Uh, as it told, this entangled photon source, pair of photons. Okay, these are pair of photons which are highly correlated, and one of the photons is being sent to one ground station, another is to different ground station, and you can measure at both the station and develop the key. So you can see that here satellite is not having any information about the key. Satellite is having just an entangled photon source, and satellite is sending photons to the ground station. So this kind of communication when you do with satellite, it's called untrusted node. You don't have to trust on the satellite. Like, okay, nobody can, even if somebody hacks, they can't have information about the key. Okay, it's not being there in the satellite. So one can have both satellite as a trusted node and satellite as an untrusted node. And in one case, one uses entangled photons. In another case, one uses weak coherent pulses or single photons. Okay, we'll talk what is weak coherent pulse. We'll discuss as we go on. And what is single photon source and how you make entangled photon source. We will discuss as well. So already I have told this no cloning theorem. Arbitrary quantum state cannot be cloned. Okay, this is one of the principles that provides security to quantum key distribution. Another principle is you are using like Heisenberg uncertainty principle, where you talk of conjugate variables. Okay, if you have, you can't have accurate information when you are measuring two conjugate variables at the same time. Hmm? If they are being measured simultaneously, you can't have um, correct information, perfect information. So you take this mutually unbiased basis, where these are formed by like conjugate variables in one basis, another basis will have conjugate variables. Okay, So suppose in case of photons, you can ascribe horizontal and vertical. Polation is basically a two-state basis. Okay. If you know the two polation states, you can talk of all the polation states. Okay. So polation is two-state basis. So if you are preparing these photons as a diagonal polarized light, okay, and you are measuring in another basis, horizontal and vertical, that is called linear basis. This is diagonal basis. Okay, if you are measuring in horizontal and vertical, some half of the times you will get randomly, like random results. Sometimes you will get horizontal, sometimes you will get vertical, half of the time. So you can't have any information. You have prepared a photon in diagonal. If you get diagonal identical, then only you can have information about the correct information. But here you will get random results. Same if you have prepared your photon in horizontal polarization. What I mean by preparing photon in horizontal or diagonal, just it's a photon is light signal. Okay, um, it passes through a linear polarizer, which is diagonal, which fast axis is diagonal. So it will give you diagonal polarization. After passing through, it will become diagonal. So that's the meaning when I say it's a diagonal polarizer. Same way, if it is horizontal, this polarizer is like horizontally, fast axis is horizontal. So you have prepared a photon in horizontal state. And suppose you have prepared your photon in horizontal, and this was a linear basis. Linear basis, when I say it has two states, polarization state, linear basis having two polarization state, H and V. And we say I say diagonal basis, it's having two polarization states, D diagonal and anti-diagonal. And the photon prepared a horizontal, suppose you measure in this diagonal basis, you will get random results. You can't have you you won't get useful information. Randomly you will be getting diagonal anti-diagonal polarization when you measure with linear polarization. So this is very important. So these are the two things very important which provide this security to quantum key distribution. Another thing which is very important is like bound, error bound. Okay, you can fix the information leakage, like how much information leakage you can tolerate or how much error you can tolerate. Leakage is equivalent to error. How much leakage or error you can tolerate in a system. Like here you see this is secure key rate, okay? R is secure key rate, and this is binary entropy, which is defined like this: X is random variable. And here, if this is error rate, okay, bit error rate. If this bit error rate becomes 11.2%, you will not get any secure key. Okay, so you have upper bound. So if there is information leakage or error, you will not get secure key or you will not get key. So that is another very unique property when we are using quantum key distribution uh, for secure communication, which is not there in classical communication. Anybody can tap and you don't know how much. You can't fix that information leakage. Okay, because you're using boosters, you don't know how much information is being leaked. Okay, that's why this I talked of this store now and decrypt later. Okay, these things are there when you're using classical. So here I will stop for some time and I invite questions. Okay, and then I will go further. Do you have questions? Any one of you having questions? Hello.
Yes, sir. So let me check
Tell
if there is any question. No, sir, not so far any question. So if you want, you can continue. We can take
Do
five
you have
minutes
any
break.
question? You yourself is having any question? You also are not having any question.
Okay.
Do you have any question? Or others are there online? They can unmute themselves and ask question if they want.
No, no,
It's
it's a
not there. It's
yeah,
not essential
participant.
to write question in the chat box. Yeah.
Yes. Okay, so
Nobody
there is
is.
one question, sir.
Mhm.
Can you explain mutually unbiased basis?
That's what I was trying to explain. So suppose this horizontal and vertical, this linear and diagonal basis, they are mutually unbiased basis. There can be one more, when we talk of polarization, there can be one more mutually unbiased basis, like um, left circularly polarized right and right circularly polarized. I'm just taking two mutually unbiased bases here. So these are the mutually unbiased bases. In the sense, suppose you are encoding in this diagonal basis, and you measure this in linear basis, you will get random results. You can't have correct information. Same way, if you prepare in this horizontal or linear basis, and you measure in diagonal basis, you will not have any information. Okay, you will get random results. That's the meaning of mutually unbiased basis. Fine.
So there is one more question, sir.
Okay.
Does the current satellites are having the capability to participate in the QKD?
Satellites, there are not many satellites, only China is having satellites, okay, two, three satellites which can do this, which are capable of doing quantum key distribution. Other countries are planning, okay, to have this satellite-based quantum key distribution, but it's still no country other than China is having a satellite-based quantum key distribution. All the satellites can't have. You have to have payload for like quantum state generation or entangled photons, and you have to have ground station which can receive this signal. Okay, so like existing satellites which are there in the orbit, and they can't do this quantum key distribution. You have to like prepare or make your satellite capable, and ground is capable of quantum key distribution, which is still not there. Other than China, no other countries having like this kind of facility, ground stations capable of receiving the quantum signal and satellites beaming the quantum signals.
Okay. So there are
Okay.
more questions. So I will dictate.
Okay.
So do we multiply R? Do we multiply R with the transmission rate to we get the secure key rate?
This R is secure key per bit. Okay. So suppose you're sending 1 qubit. So what will be the secure key out of that? So suppose you are sending 1000 bits. Okay, 1000 bits you are sending, but you may have like secure key maybe only 30. Okay, so per bit like you have only this much of secure key, so that you can calculate. It's not like multiplication and all those things. Yeah.
Okay. So yes, so there is one question on the current slide which is displaying.
Okay.
So there is a yes. So this is Dr. Souvik Roy. He's asking if H vector is horizontal and V is vertical, then
Yes.
the D is diagonal. What does A stands for?
Age anti-diagonal. Suppose is 45 diagonal, 135 will become anti-diagonal. That's what. Hmm.
Mhm. So there is
All are
one
linear
more question.
polarization. Okay, one horizontal,
Yes.
vertical, diagonal, and all are linear polarization.
So there is one more question, sir. Why
Yeah.
we are doing this in the satellite? Can't we have a direct ground key distribution?
We can have, as I told already, you can do with fibers, okay, but long distance fiber key distribution is not, quantum key distribution is not possible, because we will lose the signal and we can't use amplifiers, okay. So that's why this long distance quantum key distribution using fiber is not possible. That's why we have to go for satellites for long distance quantum key distribution. I discussed this point in earlier slide. You can see that. I think yeah, here I discussed. Okay. Anyway, so what is any other question?
Yeah. So one question from my side, sir.
Mm-hmm.
So as you said in your talk that, okay, we need a single photon. Let's say we are taking single photon from SPAD, single photon avalanche diode, and then there is a QKD link attached to it. If I made this system for, let's say, 5 years mission satellite, the space mission, if I'm sending this to for the 5 year space mission, due to the radiation, what would, like, can you elaborate, like, is the QKD links will also need have some effect of those radiation which is inside the space?
So you seal your payload. There are many payloads are being sent to the space. This is not like so you have to seal your payload to safeguard against radiation. So most of the payloads, okay, like almost all the payloads are shielded, okay, against radiation damage. So this also has to be shielded for radiation damage, okay, and depending on shielding, it will have like life in the space. So it has to be shielded against radiation damage. We use some metal sheets, okay,
Yes.
to seal that. Fine.
Okay, so one more question, sir.
Mm-hmm.
Can you go up?
Yeah.
Yes. When the satellite is used as a photon source, there is a
Mm.
high scope for the disturbance due to the interaction of photon with the other atmospheric particles.
Okay. So
How
as
is the how is the key transmitted without losing the information?
okay. So you will be losing photons certainly. Like in fiber also you lose because fiber has attenuation, as I told you. That's why you don't use fiber for long distances because you can't boost the quantum signal. Okay, because you can't clone the quantum signal. Same way in satellite, when you are sending photons, there will be losses. Okay, that's why you suppose you are sending 10 power 6 photons per second from satellite, you will have hardly 10 power 3 or 10 power 2 photons. Okay, per second at the ground station. So you will be losing. That is not a problem, but once you measure the population state, so key generation rate will be less. That's all. You will be losing photons on the way, certainly. And either you do fiber or satellite, you will be losing photons. Okay? All the photons transmitted will not give you the key. You will be losing photons on the way.
There is one more question, sir, for you. Uh,
Yeah.
why cannot we use the amplifier, and what is the reason, sir?
I am repeating again because no cloning theorem doesn't allow to make copies. What you do in amplifier, you make the copies, you boost the signal by making the copy of the signal. Okay, that's what you do. Okay, so but you can't do the copying, so you can't boost the quantum signal. Okay, so you can't use amplifiers there. That is the problem. No cloning theorem doesn't allow you to use amplifiers in quantum key distribution or quantum communication. Okay.
There is last question, sir. How can
Mhm.
entangled Bayes algorithm be achieved in satellite channels, particularly when it requires entangled extension, swapping, etc.?
So entanglement swapping is further stage when you want to have this quantum communication network. But by keeping entangled photon source, shielding it against damage, radiation damage, one can send like entangled photons to the ground station. Not a problem. It is already being done by China. They have demonstrated, they published the results. So one can send entangled photons to the ground, and one can have measurement of those photons, and one can have key, and one can verify other properties like whether they are still entangled or they are not entangled. Once you have entangled photons, one can have quantum teleportation, because um, for quantum teleportation, entanglement is a resource, and using entanglement as a resource, you can send a quantum state from one place to another. So that also one can do. So all those things have been demonstrated already by China, and China is undisputed leader when it comes to quantum communication.
Okay, sir. So we will take, thank you, sir. Now we will take, sir, 5 minutes break.
Okay, not a problem.
Okay.
Okay.
Yes, yes. Thank you, sir.